Well, it is a true honor to be here in Oslo on the occasion of the awarding of the Abel Prize to John Milnor. As you all have heard, Milnor has made outstanding contributions to a broad range of mathematical disciplines. In this talk, I just want to give a glimpse of Milnor's impact on two mathematical fields, namely the theory of manifolds and the theory of dynamical systems. And a unifying theme will be that unexpected phenomena, such as strange attractors and exotic spheres, actually occur naturally from simple polynomial equations. Okay, so let me start with some remarks on the theory of manifolds to set the stage. So here's a question I think we all know the answer to. Can you knot a piece of string by lying it on the table and making it into a loop but never crossing itself? Well, the answer is no. No matter how you wind a piece of string around on a table, it's never actually knotted. You have to lift it up and use three-dimensional space. And even this intricate labyrinth-like pattern is, from a topological point of view, the same as an ordinary round circle. So here's a somewhat more interesting question. Can you knot a sphere in space? So instead of trying to knot a circle in the plane, try to take a two-dimensional sphere, a bubble, and somehow deform it to make a knot in three-dimensional space. Now, somewhat surprisingly, the answer is yes, as was shown by Alexander in 1924. So here's an example of a sphere which is knotted in space. So what you're seeing here is a sort of potato-like shape which reaches up and forms two hands which come to almost clasp each other, and then the fingers of those hands each break into two fingers, and then those break into two fingers, and so on. And this object is topologically a sphere, and yet it's knotted in the sense that the complement of the object, for example, is not a disk. It's not simply connected. You can't deform this in the ambient space of R3 to turn it into a standard round sphere. Now, yes?
I think your microphone fell down.
Oh.
Here we go.
Okay. Now, one objection you might make is, well, that's not what I meant by a sphere. I mean, this is some wild object. A sphere should be smooth. It should have a tangent plane at every point, as Milnor described at the beginning of his talk. There's a distinction between sort of wild spheres and those which are smooth, that are naturally objects of calculus, that are given by simple algebraic equations. So one might ask the question in the language of what is now called differential topology, namely, is a smooth two-dimensional sphere in three-dimensional space ever knotted? And then the answer is no. There are no smooth spheres, knotted smooth spheres in three-dimensional space. So I draw this picture to give some of the impetus for the development of differential topology. Namely, differential topology rules out this kind of wild topological phenomena that's admitted if we just talk about continuous maps and homeomorphisms. And differential topology makes our pictures locally well-behaved, whereas this picture is well-behaved near many points, but it's very wild near these places where the fingers have become infinitely complicated. So we rule out that kind of pathology. And the pioneering developers of this theory of smooth topology, or differential topology, include de Rham and Whitney and Milnor himself. Now, in fact, I learned some interesting things about the history of the interactions between the theory of topological manifolds and the theory of smooth manifolds by studying Milnor's collected works. So, for example, it seems people did a lot of mountaineering back in those days. So Alexander, who produced the sphere you just saw, and de Rham, one of the developers of the theory of differential topology, exchanged ice axes when they were climbing the Aiguille de Dreux in Chamonix. In fact, they were in two separate parties. They scaled the glacier, then they planted their ice axes in the snow, and by prior arrangements did their traverse on the rock, and then went down with each other's ice axes. later returning them without ever introducing themselves. And then later, de Rham ran into Alexander and Whitney on the Weisshorn in Valais, 1933. And as far as Milnor is concerned, he reports that he and Whitney climbed the Mexican volcano Iztaccíhuatl in 1956. And then finally in 1966, de Rham and Milnor climbed the south ridge of the Stockhorn. So let me go back to 1956. So this wasn't the only thing that happened. So as you've heard, this was the year that Milnor discovered that there is a smooth manifold of 7 dimensions that is homeomorphic to the sphere, but not diffeomorphic to the sphere. So just to give you a picture of this idea, which you've already heard, if you have a manifold which is smoothly the same as a sphere, well, smooth maps are locally like linear maps. So if you imagine that you take a little piece of this manifold and you cut it into pi slices, these pi slices have to continue to match up perfectly, even if the boundary of the pi is turned into an ellipse. Whereas in the topological or PL case, you are allowed to take these pi slices and reshape them. You can have sort of cone-like singularities at the center of this map, and that kind of singularity might or might not be something that you could make smooth again. So in fact, there is a map that squeezes the pi pieces and turns this manifold topologically back into a sphere, but there is no map that smoothly retrieves this spherical structure. Now, let me give you a little context for Milnor's surprising discovery. Well, first, I'd also like to make a historical remark on the Poincare conjecture or higher dimensional Poincare hypothesis. I would tell the history slightly different than the way Milnor presented it. I would say the first progress on this conjecture was by Milnor, and he proved that the smooth Poincare conjecture is false in higher dimensions. That is, if you try to recognize a 7-dimensional sphere by the standard techniques of algebraic topology, well, there's some algebraic tests you can apply to such a gadget to test if it should be a sphere. It should be simply connected, so we check its fundamental group, and it comes out to be the same as the sphere. And then we compute its homology groups, which are even easier, and they turn out to be the same as those of the sphere. And yet, this algebraic information is not enough in dimension 7 to guarantee that this 7-dimensional manifold is diffeomorphic to a sphere. So to put this in context, let me just say a few words about lower dimensional manifolds. So the classification of 2-dimensional manifolds is familiar. The orientable ones, the closed 2-dimensional manifolds, look like a sphere or a donut or a 2-hole donut. They're classified by their genus. But an elegant way to say this theory in terms of algebra is that a 2-dimensional manifold is determined by the inner product space, the middle dimensional cohomology H1 of M with coefficients in Z mod 2. So the picture you should have of this space is the following. So we attach to this, one of these topological objects, an algebraic object, and the elements of this space should be thought of as loops on your surface. And then when you have 2 loops, say this yellow loop and this black loop, well, then you can count the number of points where they intersect. So in this picture, those loops intersect in exactly 1 point. And that gives an inner product structure to this space of loops. And if you only record the parity of the number of intersections, that is, if it's 0 or 1, then you get an inner product space with values in the field of 2 elements. And the theorem is that this very simple algebraic invariant contains the same information as the number of holes of this surface. It detects whether or not the surface is orientable. And so it suffices to classify 2-dimensional manifolds. Now you'll notice in Milnor's lecture, he also talked very much about 4K dimensional manifolds. Even dimensional manifolds tend to be more amenable to classification in some ways because of the presence of this kind of intersection form, 4K dimensional ones especially. So let's go to 4 manifolds now. So for a 4-dimensional manifold, one can do something very similar. Namely, you can take the surfaces inside of a 4 manifold, that's the cohomology group H upper 2, you can count the number of points in the intersection of two of them, and that also determines an inner product space. And we can also require that these manifolds are simply connected, their fundamental group vanishes, and then there's really no other evident invariant of algebraic topology to attach to such a manifold. So you have an inner product space on a finite dimensional Euclidean space of finite power of the integers. And in fact, Milnor proved in 1958 that a simply connected 4 manifold is determined up to homotopy equivalence by this inner product space. Well, let me say a few words about manifolds in general before we plunge into some theoretical results. One question you might ask yourself is, where are these manifolds coming from that we're studying so intently? Where do manifolds come from? So here's one source of many different manifolds. And as I mentioned, one of the themes of this talk is that these basic mathematical objects can often be nicely described by simply polynomials if you use complex numbers. So one way to make a two-dimensional manifold is to take an equation, say x to the d plus y to the d equals 1. Think of this as an equation in two complex variables. Well, then it describes a surface in a two-dimensional complex space, or rather a curve of one complex dimension. And it turns out that the shape of this subspace of C2, when appropriately compactified, depends only on the degree of this equation. So if you give me an integer d, it determines some kind of surface. And in fact, we know many of these surfaces well. The case d equals 1, a linear equation determines a line, but you compactify it to make it into a projective line or into the Riemann sphere. And so the equation x equals 1, or x plus y equals 1, determines a topological object over the complex numbers, which just looks like a round sphere. And interestingly, in this dimension, for d equals 2, a conic also determines the same shape. X squared plus y squared equals 1 determines over the complex numbers a topological 2-sphere. But cubics already give rise to a torus, a surface with one handle. And the fourth degree equation, in fact, skips genus 2 and goes directly to a surface of genus 3. So in any case, many of the manifolds that appear in two dimensions arise naturally from simple algebraic equations in two variables. Well, what happens if we go to 3 variables? So then we will be describing a two-dimensional complex manifold in a 3-dimensional complex space. So it gives 4 real dimensions. And again, these manifolds are uniquely determined up to diffeomorphism by their degrees. So the simplest ones, the first 4 that arise, are the complex projective plane, and then a quadric, which is a product of 2 spheres, or 2 CP1s. The cubic surface is famously the blow-up of the plane at 6 points, so it can be described as a connected sum of copies of the projective plane and its complex conjugate. But already in degree 4, a quartic surface in space, well, it has quite complicated topology. And we pretend we understand what it is by giving it a name. It's called a K3 surface. But it's quite rich in structure. How can we try to classify these objects? Well, let me just tell you what the corresponding quadratic forms are. A quadratic form is just a symmetric integer matrix. For the case of CP2, the quadratic form is the 1-by-1 matrix with 1 on the diagonal. It's always unimodular. It's the so-called hyperbolic plane with 2 1s on the off diagonal for the quadric. For the cubic surface, it has 1 plus 1 and 6 minus 1s on the diagonal. But for the K3 surface, well, it's pretty complicated. It's a 22-dimensional matrix, which I haven't written down, but it can be obtained in a block diagonal form by putting in 6 blocks that looks like this H, and then 2 of these special blocks coming from E8, which is an extraordinary sphere packing in 8 dimensions. So when written in this way, the K3 surface looks like an extremely complicated object. It has 22 holes in it, fitted together in some extremely tight fashion. On the other hand, and this is, I think, one of Milnor's key observations about this subject, there's a much easier way to say what these quadratic forms are. Namely, they have a signature, or I should say more precisely, they have a type, PQ, the number of plus eigenvalues and the number of minus eigenvalues. And that's this integer here. So this is a +1 form. This is a form of signature 1, 1, signature 1, 6, signature 3, 19. And other than that, these unimodular forms are classified by simply saying whether or not they're even or odd. There's one additional invariant. And so the K3 surface is really just giving the even form of signature 319. And in this way, one can explicitly describe the intersection forms on all of these complicated looking four manifolds, which, however, arise very naturally from polynomial equations. Okay, so let me take this a moment then with these examples in mind to just reiterate a couple of facts that surfaced in the previous talk. So what can we say about the classification of four-dimensional manifolds? Well, the work of Friedman and Donaldson shows the following. The first is any inner product space can arise as the middle dimensional cohomology of a four-dimensional manifold. And what Friedman showed is that, moreover, it can arise in at most two different ways. So the giving an inner product is almost the same as giving a four-dimensional manifold. And this is quite surprising because in the previous list, we didn't see, for example, the E8 form sitting by itself. We saw it deep inside of a K3 surface. But Friedman showed that there exists a topological manifold whose intersection form is E8. On the other hand, from the smooth perspective, well, here we see an echo of Milnor's construction of the many differentiable structures on the 7th sphere. There's an echo of that paradox in lower dimensions. Namely, Donaldson proved that there exists topological M4s. Well, more properly, I should say, Friedman and Morgan. In any case, in this circle of ideas that developed in the 1980s, it was shown that there exist topological M4s with infinitely many smooth structures. So the 7th sphere has analogs, although of a different nature in 4 dimensions. And finally, I want to mention that there's plenty of open problems in addition to the one that Milnor alluded to. For example, you've just seen a bunch of 4-dimensional manifolds, CP2, S2 cross S2, and K3 surfaces. It's an open problem to show that by taking connect sums of these objects, you get all the possible homotopy types of smooth 4-dimensional manifolds. Okay, so now let me turn to the impact of some of Milnor's work by describing some odd-dimensional manifolds. So how can we get odd-dimensional manifolds working over the complex numbers? Well, this is another topic which Milnor developed. It's the interaction between the theory of singularities of complex varieties and knots. So here's a very simple example. We take, again, an equation in 2 complex variables. So this defines a curve in C2, and then we intersect it with a 3-dimensional sphere. Of course, everything's drawn in 1 dimension less here. And it turns out that because this curve is singular, that is, it has a cusp at the origin, the intersection, while being a smooth circle, is embedded in this 3-sphere in a complicated fashion. It actually is knotted. So this intersection between the locus defined by this equation and the locus defined by the norm of z is equal to 1 is what's now called the Milnor link of this isolated singularity. And in this very simple case of an isolated singularity of a curve, it's just a circle. But what's interesting about it is that the knottedness of this circle reflects the singularity of this curve. Well, what happens in 1 dimension higher? So interestingly, this 1-dimensional object becomes 3-dimensional if we go to 3 complex variables. And in fact, it's almost never a circle. It's usually has infinite fundamental group. And what Milnor proved is that, nevertheless, the resulting 3-dimensional space is always a geometric three-manifold. That is, it's the quotient of a three-dimensional Lie group by a discrete co-compact subgroup. And I should say that this kind of description of three-dimensional manifolds is what underlies the Thurston geometrization conjecture and all of the subsequent developments in that area. They aim to give every three-manifold a description of this type. However, equally striking, or perhaps even more striking from my perspective, is what happens in yet higher dimensions. So if we boldly go to five-dimensional space, well, here's a very simple equation that can be written down using 5 complex variables. And when you take the corresponding Milnor link, it turns out to be an exotic 7-sphere. So here's a description of this almost unbelievable object discovered by Milnor, which you can write down on the corner of an envelope and carry around in your pocket, hand to someone else. By the way, this is homeomorphic but not diffeomorphic to a sphere. That's a very succinct description of it. So I think one of the remarkable features here is that these so-called exotic objects actually arise very naturally in mathematics. They're not man-made. They're something that was waiting to be discovered. And I should also say that the basic reference for this theory of isolated singular points of complex hypersurfaces is one of the many masterpieces of mathematical exposition authored by Milnor. And in fact, like many people, I first learned the name Milnor by becoming acquainted with just a number of orange books, or occasionally yellow or blue, all of which were masterpieces of mathematical narrative. And what one finds reading these books is there's a keen sense of mathematical history and what has gone before and what is going now. Moreover, the theory is presented with a kind of inevitability that makes it look a little more effortless than it actually is. And finally, the author seems to have a keen sense of not just the past of mathematics, but of the future, because the foundations which are laid also point in the directions of what are still very active and very important areas of mathematical research. Okay, so let me use that as a moment to make the transition to my second topic, which is the theory of dynamical systems. Now, the theory of dynamical systems has many roots. The mathematical theory probably goes back to Poincaré and his study of celestial mechanics, the three-body problem, and allied questions. Let me try to connect this theory to the theory of manifolds that we've discussed so far. So one modern way to describe the theory of dynamics is that one studies a map of a manifold to itself, which might have various qualities. It might be continuous, smooth, analytic, complex analytic, symplectic, etc. And one studies the evolution of points under this map. That is, you pick a point x, and then you compute f of x, then f of x, and so on. This is called the forward orbit of the point x. And you can think of this mapping f in the following way, in the setting of celestial mechanics. So M is the manifold that describes the positions of the planets today, and F tells us, given the position of the planets today, where they will be a year from now. And then as you iterate this map, you get the long-term behavior of the orbits in the solar system. Now, there's another thing I'd like to say about this discussion of dynamics. You see, imagine that we were talking about the theory of vector spaces instead of the theory of manifolds. The classification of, say, finite dimensional vector spaces over the reals is pretty easy. They're classified by their dimension. But if you take a map of a vector space to itself, it can have a very complicated structure. It has eigenvectors, or it may not have eigenvectors. It has a Jordan normal form. The vectors in the vector space all start looking different from one another. And there's a rich and complicated structure of invariance. And in the same way, while the classification of manifolds is already extremely difficult, the classification of maps of a manifold to itself is another order of magnitude. Now suddenly all the points on the manifold take on a different meaning. Some might be periodic, some might not be periodic. There's all sorts of invariants we can attach to their long-term behavior. Okay, so with that in mind, let me discuss the theory of attractors. This is one of the simplest things you might want to understand about a dynamical system, is what happens to most points over a long period of time, over many iterations. And perhaps the simplest thing that could happen is that this map might have an attracting fixed point. That is, there's a point in your space which is fixed by the map, and nearby points converge to this point under iteration. In that case, it would be fair to say that this point is an attractor for the dynamics. There's some sort of stable equilibrium attached to this point. However, there can be much stranger objects than single points, which nevertheless play the role of attractors. So this is a picture of a quite complicated Lorentz-type attractor, and you should imagine that many points spiral towards this attractor, but they don't settle down to some stable equilibrium, but they enter some sort of quasi-periodic regime which needs to be described. And in fact, this picture begs the question of what is an attractor for a dynamical system? And indeed, I think that this question wasn't even systematically addressed correctly until Milnor's work in 1985 on the concept of an attractor. So he gave the following definition. An attractor is a subset of a manifold which is closed, and once you have a closed set, you can look at its basin, the set of points which are tend to it under forward iteration that evolve towards it in future time. And then we say that this set is an attractor if its basin has positive measure and if it's minimal in a certain sense, namely the basin of any proper subset should have smaller measure. And one thing I like about this notion is that, well, the theory of dynamical systems certainly evolved from physical theories, and this definition of attractor combines some topological ideas and some almost physical ideas. You see, one could just look for small invariant sets of the map or something like this, but if you're actually testing or studying this dynamical system on a computer, or if it represents something in real life, you only care about an attractor if it attracts a set of positive measure. You only care about an attractor if there's a positive probability that your experiment will give you an orbit which evolves towards that attractor. And so one of the nice features of this definition is it captures exactly that notion by mixing this measure theoretic condition with the topological condition of attraction or convergence. Okay, so to get some idea of how rich the theory of dynamical systems is, I'd like to talk about dynamical systems on one-dimensional manifolds. So here's a very simple experiment that we can carry out on a one-dimensional manifold. It's the simplest experiment, really, you can imagine after the theory of linear maps. So what we're going to do is we're going to iterate the transformation, x goes to x squared minus c, on some invariant set, which will, in this case, just be an interval on the real axis from minus c to c. And we're going to try to see what the attractor of this dynamical system looks like. Where do most points converge? Now, I like to think of this dynamical system as a new kind of financial instrument. So I give you an investment, which rather than doubling or tripling your money, I promise to square whatever your balance was. So you give me x. Next year you get x squared in your account, but I subtract off a small commission, c, for my trouble. And so you wisely invest $0, and then the next year you're minus c in debt, but the square of a negative number is positive. So you go to c squared, and then we continue evolving in this way, and you see what happens to the balance in your account. And it turns out that for small values of the commission, if you invest 0, well, then your account rapidly converges to some specific stable value. But as I gradually increase my commission, this investment becomes, well, a little bit less reliable. In fact, for larger values of C, it turns out that your balance will fluctuate back and forth periodically between two values. So in the first case, the attractor is a single point, but for a larger value of C, the attractor is 2 points. Well, let's look at the whole portrait of what this attractor looks like as the commission C gradually increases from 0 to 2. Well, here's the picture. So the cycle of order 2 splits into a cycle of order 4, and then a cycle of order 8, and so on. And then finally, something very dramatic happens. One says there's the onset of chaos, and the attractor becomes quite wild. It might fill out several intervals on your axis. It might or might not have some sort of invariant measure. So there's a really rich spectrum of behavior taking place for large values of C. Now there's something, let me just zoom in on this a little bit so we can see better what's going on. So there's a cascade of period doublings taking place here. So 2 goes to 4, goes to 8, and so on, as I just said. But then up in this chaotic-looking region, well, you see sort of islands in the storm, this one being particularly prominent. And they seem to be occurring everywhere. Also, there seems to be a lot of structure in this transition from periodic behavior to chaotic behavior. Physicists would describe this as a phase transition and try to extract various universal constants from what goes on as we cross through this transition. Well, to really illustrate the true richness of the subject, what I'd like to do is take this window up here in which there is a cycle of period 3 and blow it up for you again. I'm going to focus just on this central piece of the window. And what you see is this. So within this window, there's a recapitulation of the entire structure of the whole picture. That is, there's a cycle of order 3, which bifurcates into a cycle of order 6, and then of order 12, 24, and so on. And then, again, the entire complexity of the chaotic regime seems to be replicated in its exactly the same form as in the global picture that we started with. So this is the remarkable feature of self-similarity in the bifurcation patterns for these dynamical systems. Now, I want to make just one more remark. Something I realized listening to the last talk is that one way to think about what's going on when we go from period 2 to period 4 to period 8 is that we are forming a connected sum between different dynamical systems. And I'm going to further explore this notion of connected sum as we proceed. But I just wanted to mention that this idea that was discussed about taking an S2, connect sum, or an Sn, connect sum Sn, connect sum Sn, and taking a limit of these gadgets is really the same motif in a different way, which appears in this cascade of period doublings. Namely, we somehow take a dynamical system with a cycle of period 2 to the n, and then we connect sum it with a dynamical system of period 2, and the result is period 2 to the n plus 1. So this universality and this phase transition is somehow the result of an infinite connected sum of dynamical systems. Okay, so now to a theoretical investigation. So in the late 1970s and early 80s, Milnor and Thurston made a really seminal contribution to the theory of this kind of topological folding map on the interval. So let me just give you a hint of what they studied in this work. So one invariant you can attach to a map of the interval to itself, like x squared minus c, is the following. Well, let's really investigate the iterates of the map. So here's the graph of the function f. Here's the graph of the function f squared. Here's the graph of the function f cubed, by which I mean f composed with itself 3 times. And what you see is this, well, I learned that this is called knoteri in Norwegian. You see this kneading behavior. We fold the interval over and over itself. There more and more laps develop. And it's interesting to count the number of laps as a function of the number of iterates of the map. The number of laps meaning the number of branches of this graph that go up or down. And in fact, there's a very rich topological complexity to this very simple looking folding map. And to capture and organize that complexity, Milnor and Thurston introduced a lot of motifs that are absolutely fundamental in the discussion of this subject. So let me just say a few of them. One is the kneading invariant, which is just telling you for each iterative f whether the center of the graph comes above or below the x-axis. So that's a sequence of plus or minus ones. We can also ask just about the topological dynamics, to what extent are two of these systems topologically the same. We can count the growth of the lap numbers, or what's called technically the entropy of the map. And we can also look for the number of fixed points of f to the n, or the number of periodic cycles of period n, and try to organize all of this information. So just as a glimpse of what these authors were able to carry out, they defined a formal power series called the kneading determinant, built out of these kneading invariants. They compared this to the zeta function, which counts the number of fixed points of f to the n, and they proved this very simple and beautiful formula that the zeta function is simply the reciprocal of the kneading determinant. Equally fundamental was sort of a qualitative study of the dynamics. Namely, they took all of the possible kneading behaviors and gave them a total ordering, and then proved an intermediate value theorem that said if you go from this dynamical system to that one, then you have to go through all of the dynamical systems in between. And for example, it's easy to verify that the dynamical system x squared minus c contains the simplest kneading invariant and the most complicated one, and consequently it has to represent every possible topological behavior. And indeed, when the map has a periodic cycle, and this periodic cycle bifurcates, the same principle shows that the entire kneading diagram reappears at a smaller scale within the original picture. So this gives a sort of topological explanation of the self-similarity which we have seen. Now I'd like to just say a word about how you can imagine that the author of the exotic 7 sphere was also the author of this paper on dynamical systems. Namely, one way of saying what this theorem says is it says that each topological f, that is, each model for this complicated kneading behavior that you can think of, actually arises for a smooth mapping. Or to put it differently, if you start with a topological dynamical system, it can be given an invariant smooth structure, at least within this simple theory of kneading maps on the interval. And so it shows the existence of an underlying smooth structure on each of these topological structures, but it shows something much more striking, in fact, namely that there exists a quadratic polynomial that is an algebraic dynamical system which realizes the given topological dynamics. Well, now I want to talk a little bit about the repercussions of this important work of Milnor and Thurston's. It really set the stage for an explosion of research in complex dynamics. So we simply continue to study this map x squared minus c, or maybe x squared plus c. But what do? Well, we change the c to a plus c, and then we change the x to a z. And the z means that we study the behavior of this mapping on the complex numbers. So both z and c are allowed to be complex. And then again, we can look for the behavior of attractors, for example, for these polynomial maps of the plane to itself. And this new discussion includes the previous discussion as a special case, but it also contains a very rich collection of new objects. Okay, so what is the Mandelbrot set? The Mandelbrot set is a fundamental object in the study of these quadratic polynomials. It's defined to be the set of C such that the orbit of z equals 0 is bounded under iteration. So this means, in the investment metaphor, that the balance in your account does not go off to infinity, even if you start by investing just $0. And this turns out to be a necessary condition for there to be any attractor for this map in the complex plane. So rather than giving a full discussion of complex dynamics, I just want to describe some of the structure of the Mandelbrot set and relate it to what we've seen already. So first, let me point out that the real axis meets the Mandelbrot set in the previous discussion. So if the value of C turns out to be real, then we're discussing just the real polynomials that we were talking about before. And there's a perfect correspondence between points in this bifurcation diagram and the shape of the Mandelbrot set. So for example, this regime here, where there was a unique attractor, that corresponds to what's called the main cardioid, this big blue piece of the interior of M. The period doubling cascade corresponds to this stack of bubbles, the main cardioid, then the next bubble, period 2, period 4, period 8, and so on. This phase transition is what's called the Feigenbaum point. It's at the tip of that stack. And then all of these windows correspond to other structures that are seen here along the real axis. But of course, there's lots of other interesting stuff seen off of the real axis. Well, how can one even attempt to organize all of this structure? So let me tell you one of the organizing principles and some of the conjectures that have been put forth on this subject. So there's a very influential paper of Milnor written in 1986 called Self-similarity and Hairiness in the Mandelbrot set. And it's about this behavior that we already saw over the real numbers, namely that the whole bifurcation diagram reappears within itself in infinitely many places. So to see this self-similarity over the complex numbers, what I'm going to do is blow up the Mandelbrot set around a not completely randomly chosen point near the boundary of the main cardioid. Okay, so let's do a little blow up of this picture there and see what the fine scale structure looks like. Okay, so as we go towards here, this is sometimes called the Sea of Elephants because there are these trunk-like shapes climbing up this white wall, one almost grasping the tail of the next. Now we're going into the eye of one of these elephants, and then into one of these features which grows off of that eye. And then now here you see this eye sort of has split into two pieces. And then see there's also some sort of complex doubling thing going on here. Now there's 4 pieces here, and then at a smaller scale, 8, and then 16, and then we see a copy of the Mandelbrot set itself. Now, one picture I want you to imagine is that we now find within this small copy of the Mandelbrot set exactly the same point that we've zoomed in on already. And we iterate this process. So we zoom in again at this point, and we find a much, much tinier copy of the Mandelbrot set. And we continue carrying out that process. So that's a form of this infinite connect sum that's called in the dynamical setting renormalization. Well, my next slide describes what is believed to happen if you do these iterated blowups, if you do these so-called renormalizations. So this was conjectured by Milnor in this paper. What he conjectured is that the magnifications of the Mandelbrot set near any fixed point of renormalization are self-similar, and they fill the plane. So let's do a much simpler example of these blowups. This is, by the way, these illustrations are taken directly from Milnor's paper. So here's the simplest, this is the cascade of period doublings we've been looking at. So we can blow up this small circle here and make it into this big circle here. And in fact, the picture looks almost the same, except there's a lot more of these sort of furry decorations. And then we blow up this circle here, and again, you see almost exactly the same picture, but a lot more hair. And in fact, the fact that these pictures become self-similar is a manifestation of this universality of critical phenomena and phase transitions. That's a basic motif in physics. So this conjecture captures, for the simplest dynamical system, some vast principle that underlies a lot of of contemporary physics. And indeed, this principle was finally proved by Lubitsch some 13 years later, at least for the values of C in the real axis. Now, I should say that since we are in the complex numbers, we can do something very similar to period doubling. We can do period tripling by moving off of the real axis towards this small bubble, and then within that to the next higher bubble, and within that to the next higher bubble, and the pictures get furrier and furrier. And the conjecture of Milnor obviously holds in this case as well, and yet the proof is more or less completely open. That problem remains almost completely open. There's some techniques that are used on the real axis which combine with complex techniques to establish this theorem, but what's really missing is some way to control the critical orbit in the case where C is complex. So let me conclude this discussion of the Mandelbrot set with one more picture, again related to this 1986 article of Milnor's. So here's another blow-up of the Mandelbrot set. The white parts of the picture are in the interior. The black parts are in the boundary of the Mandelbrot set, and this complicated coloring has something to do with being in the outside of the Mandelbrot set, classifying those points. So what you see in this picture is that there's sort of a big white snowman with many smaller snowmans resting on him. And then there's another little white snowman up here. And in fact, this whole set is connected, but it's connected by this extremely thin fungus, which grows from one of these objects and sort of forms a thread-like lattice that fills the plane and holds the whole thing together. And these black points are very hard to find by the most naive computer program. If you pick a point at random in this picture, you seem to have zero probability of hitting the boundary of the Mandelbrot set. And indeed, when Mandelbrot drew his first pictures of the Mandelbrot set, well, he saw these white pieces, such as this one and this one, but he didn't detect these black filaments holding the whole object together. And it was only later that Douady and Hubbard proved that the Mandelbrot set is, in fact, a connected topological space. So this filamentary structure is very rare from a sort of point of view of physical experiments, and yet it's profoundly influential on the whole structure. So let me just say a word about this. So one conjecture that has been verified in only a few cases is that the boundary of the Mandelbrot set is very thin, meaning it's very unlikely to land in this black part, but it's also very dense. That is, it's coming close to most of the points in this blown up picture. And just to give you an idea of some of the progress, I haven't even formulated this precisely, but there are precise formulations, some of which are supported by the following results. So Shishikura proved that the boundary of the Mandelbrot set is a two-dimensional object. On the other hand, it's still an open problem to show the boundary has measure 0. Okay. So let me conclude by just looking at one more aspect of the theory of complex dynamical systems. So a lot of mathematics proceeds by what I would call the method of steepest ascent. That is, you see a goal and you try to go straight towards it, and it gets more and more difficult, and the results get more and more technical, and fewer people understand them, and the whole field sort of narrows down as you try to go up this very steep path. And to a certain extent, a lot of mathematics proceeds in that way. And one of Milnor's influences in this area has been that he constantly reminded us that there were many other equally challenging and perhaps more scenic routes on the same mountain. For example, rather than studying quadratic polynomials, we could study cubic polynomials. We could study quadratic rational maps. We should always think over both the real and complex numbers. We could study polynomial maps in 2 variables, or higher degree maps on the projective plane, or automorphisms of complex surfaces, taking the next steps in this very rich theory, rather than becoming hypnotized by the Mandelbrot set. So I'd just like to touch on these last 2 topics very briefly. So here's a beautiful work of Bonifant, Davija, and Milnor from 2007. They study a dynamical system on the projective plane. All of these elegant illustrations are taken from their paper. And again, this is a dynamical system that has a very succinct description from an algebraic point of view. So it works in the following way. The sphere can be filled out by cubic curves. So a cubic curve has the property that it meets a typical line in 3 points. So if we pick a point on one of these curves, then the tangent line touches the curve twice at that point, and so it touches that curve at a uniquely determined third point. And the map which sends this point to that third point is the map we will consider. That map has a rather easily understood dynamics because it preserves this foliation by cubic curves. However, this map belongs to a family of maps where there are only 2 invariant cubics, one of which is this so-called Fermat cubic here with a very simple equation, the other of which is the degenerate cubic consisting of 3 lines, one of which is the equator here. And this picture describes the behavior of the union of this cubic and those 3 lines as an attractor in the sense of Milnor. So it describes the speed at which typical points converge to these objects. And it's quite interesting that these objects even serve as attractors. There are many dynamical systems in 2 dimensions where one has no idea what the attractors are at all. Here's another picture of the phenomena discussed that can be discussed in this example. So in this picture, there are 2 invariant circles in the real points of the picture. And amazingly, these circles attract an open set over the real numbers. And it appears to be true experimentally that these circles are the centers of what are called Herman rings over the complex numbers, and that these invariant Herman rings form an attractor for, well, an open set, possibly even a full measure over the complex numbers. It's quite difficult to even find a good way to investigate the dynamics over the complex numbers, and this is done by Milnor and his co-authors in this paper. So here's a sort of description of the behavior of the coordinates of a complex point under iteration, and you see the behavior starts out very stochastically, but then it becomes sort of quasi-periodic, and that's symptomatic of the point being attracted towards one of these invariant circles. A third example is the phenomena of intermingled basins. So in this picture, the Fermat cubic and the equator are each separately attractors. We can try to ask which points go to one and which points go to the other, and remarkably, there's positive sets which are attracted to each. These sets are, of course, disjoint, and yet they have the same closure. So what are we seeing in these examples? What we're seeing is that some of the most exotic imaginable dynamical behavior already arises for some of the simplest algebraic dynamical systems. So turning just for a second to the theory of automorphisms of projective surfaces, I'd just like to mention a problem I've been interested in, which is the study of the entropy of maps of a surface to itself. It's known that this entropy can only be positive in the case of a couple of these surfaces, the ones most of which we've already seen, these blow-ups of the complex projective plane, or these K3 surfaces. And it's been an open problem for some time to try to decide what the smallest complexity dynamical systems are among holomorphic automorphisms of these surfaces. So the torus case is actually easy. It turns out to be the log of a certain degree 4 algebraic number. For the blowup of CP2 about 5 years ago, the answer was discovered. Also, there's a log of a certain well-known algebraic number. And just a couple of months ago, I finished the case of K3 surfaces by constructing an example which also realizes the minimal entropy in this case. Now, I bring this example up for 2 reasons, one of which is that although this is an investigation in the theory of dynamical systems, it involves intimately the topological theory of these form manifolds and the theory of quadratic forms. And indeed, one of the standard references that's appealed to in this research is the work of Milnor and Huesmuller and others on the classification of quadratic forms over various number fields and local rings. One then needs to construct an algebraic model for the action on cohomology. And thus one sees a mathematical narrative arc that links the theory of four manifolds and their intersection forms through to the modern theory of complex iteration, which has been Milnor's latest concern. Well, the other reason I'd like to mention this is that this last result, it was the product of a conversation that took place at an excellent meeting in Banff just a few months ago, the Milnor Conference on Frontiers in Complex Dynamical Systems. And, well, let me just conclude by saying that it is clear from that Milnor's influence on mathematics will be felt for generations to come, and not just through his research contributions and through his iconic mathematical writing, but also through the community of mathematicians that he has helped to create. Thank you.